Hi everyone, I'll be talking about our work IRLNav, Imitation and Reinforcement Learning for Effective ObjectNav. This work was done with my collaborators at Georgia Tech and Metafair. In this work, we present an approach to combine imitation learning on human demonstrations and RL fine-tuning for effective object goal navigation. In ObjectNav, the agent is tasked with searching for and stopping at an instance of a goal category, for example, a cushion in an unseen environment. Prior works have shown imitating a large data set of human demonstration leads to state-of-the-art results on ObjectNav. We find combining imitation learning on human demonstrations and RL fine-tuning leads to agents learning effective object goal navigation. When using on-policy RL algorithm like DDBPO for fine-tuning, naively initializing RL policy using IL pre-trained weights leads to policy failing catastrophically due to destructive policy updates early on during RL training. To enable successful RL fine-tuning, we use a training regime with sparse success rewards. For fine-tuning, critic weights initialize close to zero, a two-phase fine-tuning setup with a critic learning phase where we roll out trajectories using a frozen policy that is pre-trained with IL and use collected experience to learn a critic, followed by interactive learning phase where we fine-tune both policy and critic until conversions using experience collected online. We find that naively switching from phase 1 to phase 2 leads to policy failing catastrophically. To remedy this issue, we propose a learning rate warm up and decay schedule where, after the critic learning phase, we linearly warm up the LR for the policy and decay the LR for the critic to a fixed value. Once both critic and policy reach a fixed LR, we train the policy till convergence. We use CNN plus RNN policy architecture for our experiments. Specifically, we show results using OVRL RGB architecture, which uses a RGB only input with pre-trained visual encoder in addition to GPS plus compass and goal category embedding. We compare OVRL RGB to a prior work which uses an explicit semantic predator. We find that using a RGB only baseline with pre-trained visual encoder outperforms an approach that uses a semantic predator by 10.2% on success and 4.6% on SPL. Next, we find that using our RL fine-tuning regime, we improve IL pre-trained Sensec and OVRL RGB policies by 3.4 to 5.6% on success and 5.9 to 7% on SPL. Our RL fine-tuning improvements are consistent on ObjectNav test standard and test challenge split. Our approach achieves 65% success and 33% SPL. Next, to investigate the scaling behavior of IL and RL fine-tuning, we plot human demonstration dataset size versus performance on HM3D val split. We find scaling dataset size improves IL performance, but as we scale pre-training dataset size, the improvements from RL fine-tuning are marginal. We present additional such analysis in an upcoming work. Now we take a look at the failure modes of our best performing policy. We find our approach has significantly small number of exploration failures and majority failures are due to missing annotations. Here's an example of early stopping behavior where the agent reaches close enough to the goal but calls stop action right outside the success radius because it's unable to reach the goal due to issues in CNAV mesh. Next, you can see the example of missing annotation. Here, the agent sees and locates the object, goes to the TV monitor, but it fails because the annotation for TV monitor are missing. Our agent also fails on episode where it is required to navigate between floors. Here's an example of agent not finding the bed on the current floor because it needs to navigate to a higher floor to find the bed. We quantify different failure modes by manually labeling 500 failed episodes from our best agent. Of the failed episode, 27% come from missing annotations, 21% require agent to navigate between flows to solve the task, 20% failures are due to recognition failures, so I think we need better recognition systems. 11% failures are due to early stopping, where the agent stops outside the goal success radius due to hard to navigate nav meshes. 9% failures are due to bad nav meshes blocking the path of the agent. 6% failures come from semantic confusion, where the agent confuses the goal object, for example, heading to armchair instead of a sofa. Finally, 6% consists of looping, where the agent loops over the same location instead of exploring, and exploration failures, where the agent never sees the object during an episode. Key takeaways from our work are combining large scale imitation of human demonstrations and RL fine tuning leads to effective object nav agents. RGB only policy with OVRL pre-trained representations outperforms prior semantic segmentation based ObjectNav approaches. Thank you for your attention. My name is Ram and I'm happy to answer questions over email.